Okay, so hello everyone. Today's topic that will be discussed here and in this presentation is ferromagnetic resonance theory. Ferromagnetic resonance is a prominent research area that an observable physical phenomenon occurs as a consequence of changing dynamic patterns of magnetization vector. So in this presentation, several topics regarding the theoretical background and mathematical analysis of the theory will be discussed. We will start our discussion with energetics and fields in ferromagnets and continue with the dynamic of the magnetization model. Later on, a mathematical analysis performed via MATHEMATICA tool is going to be shared. As a final discussion, some measurement techniques where ferromagnetic resonance condition methods will be introduced, which are listed as the conventional FMR technique and the vector network analyzer FMR technique. So we can start with our first topic. First topic of our presentation is the energetics and fields in ferromagnets. The interplay between the multiple interaction determines the domain structure in ferromagnets. So knowing the energy landscape created by these interactions is likewise indispensable in order to describe the dynamics. So few energy concepts will be introduced through this topic. So we can say that if there were energy gradient in a system, we would say that there is a field distribution through gradient intensified. So it can be stated that every single energetics brought about by a small interaction to the system has a resulting field contribution. The fields and energy counterparts of many interactions occurs in ferromagnetics are listed as shown. So we can say that the total effective field is connected to total energetics by a mathematical representation, as shown in the presentation. So first energy we are to discuss is the ZEEMAN energy. ZEEMAN energy is the interaction of the magnetization vector M with a uniform or spatially varying total external magnetic field. Which is notated by the H sub external. If we were to say that a system has a Hamiltonian H sub 0 due to interaction creating the Zeeman energy, we would have a perturbation term notated by the V sub M. It can be found approximately as shown, but also it can vary according to the lambda factor. By taking this overall volume, we can find the Zeeman energy overall volume. However, we need to find the energetics term which corresponds to small volume element, which is given as like this. So the another term that we need to discuss is the demagnetizing field energy. It is created by the magnetic body itself, and the reason why a magnetized body has a demagnetizing field energy is having non-local contribution due to having very long range dipolar interaction as shown in the figure. So another remark I want to state here that is the long range interaction is the source of shape anisotropy. So by solving Maxwell equations for a given body, the magnetizing field can be found and it is equal to minus n, which is a diagonal matrix including the demagnetizing constants, and it is with multiply the magnetization m. So the energetic term here is given by like this, and I want you to keep in mind that we will have the magnetizing constants for a thin wheel as shown in the presentation, which is the nz and the my components is 0 and the nx components will be equal to 1. So as a final term we need to consider is the MAGNETO-CRYSTALLINE anisotropy energy. So this phenomenon is explained by the spin-orbit interaction and orbital angular orientation linked to the symmetry of the crystal lattice. So energy of the spin is also linked. So the energy required to rotate M and the magnetization M vector from an easy axis to hard axis is given by like this, and the other anisotropy terms that may occur in a magnetic body are the uniaxial anisotropy and the surface anisotropy term. So, okay, so for all cases included, we have the all energetics term like this. So we have introduced some energy concepts which may has a contribution into our system. However, in our case, that will be explained and stepped into analysis. Some terms will be cancelled since contribution coming from the exchange energy is negligible. It is in order of the 10 to the -6, and so it is negligible in our condition. Moreover, since the radial degree of precision movement occurs in a small amount, there will be no significant change in the anisotropy energy. As a result, we can find field contributions coming by considering energy gradient and the field relation equation, which is stated in the presentation. As a result, total effective field will be equal to sum of all the terms we have, and it is equal to all the terms you have seen in this like this. Okay, so we have concluded that there will be some energy contributions and their field counterparts due to interplaying role of small interactions. So to analyze the ferromagnetic resonance case, we will continue with the dynamic model of a certain case. So we need to start with the equation of motion of the body case. Having introduced in the last section the effective magnetic field, which determines the static equilibrium orientation, we are able to introduce now the dynamical model proposed by the Landau-Lifshitz in 1935. The equation of motion of the magnetization can be best derived from a semi-classical treatment. It means that we are to accept that the motion of an electron in an atomic orbital under the influence of a magnetic field can be considered as a small current loop, and the total angular momentum is quantized according to the quantum mechanical model, where m is given by like this, which is equal to the gyromagnetic ratio times our total angular momentum vector g, and the gyromagnetic ratio is given by like this. So to obtain our first previous Landau-Lifshitz equation, we will get through fifth state by accepting the ideal case and the introducing terms that we have stated, and by taking over this overall value, we can do that because since we know we have domains in ferromagnets and they have connected to each other over all value, and our first term of the Landau-Lifshitz has appeared as shown in this presentation. So we can continue with our first term, and which is called the Landau-Lifshitz equation. So according to LL model, the total angular momentum is connected to total angular magnetic moment is connected to a total angular momentum, which is subjected to a torque resulting in a precessional motion. So in case of misalignment with respect to effective field does not correspond to experimental observation. So undamped precession theoretically possible, but it is in practice impossible. So the magnetization aligns after a finite time according to the experimental observation with the direction of the minimal energy. So Landau and Lifshitz added a phenomenological dissipation term to overcome inconsistency, but there occurred another inconsistency, which is as the time derivative of the magnetization vector goes to infinity, our dissipation term goes to infinity as our time derivative of the magnetization goes to infinity. So this damped equation is not solvable under the high damping conditions. So the Gilbert introduced another term which is called the Gilbert term alpha, and the RR equation becomes the LLG equation, and we can continue with that. So Landau-Lifshitz Gilbert equation, it consists of the same precessional term as in the Landau-Lifshitz equation, but combined with a different damping term, alpha. So while mathematically they are equivalent, the two equations do not lead to the same magnetization dynamics for infinitely high damping. So it is our Landau-Lifshitz Gilbert equation, and we have solved the second inconsistency occurred when our dissipation term had been introduced. So as the alpha term goes to zero, our time derivative of the magnetization vector goes to infinity, and it is also solvable in high damping conditions. Okay, so we can continue with the analysis part, in which we are able to define the frequency susceptibility of a given material under certain conditions. So finding an analytical solution for the LLG differential equation is not feasible in general form. It is only solvable under the some assumptions has been taken. So therefore, we resolve it for the special case under the following assumptions. So as we stated, it is not feasible in general form, so it can be resolved for the special case taking several assumptions. So what are these assumptions? These assumptions respectively so that the sample is an infinitely extended thin film located in the XY plane. Its demagnetizing factors thus corresponds to S to be Z and Y, the Z and Y components of the demagnetizing factor is 0 and the X component is 1. This is what I have mentioned in the demagnetizing field section previously. So the second assumption is the sample is assumed to have a uniaxial magnetocrystalline anisotropy with an z-axis in the x direction, where the anisotropy field is much lower than our saturation magnetization. A uniform magnetic field applied along the x-axis leads to a homogeneous magnetization in the same direction. A small alternating RF excitation field, which is our microwave field that's created by a microwave source pointing along the y direction, and it is perpendicular to external field, gives rise to uniform small amplitude precession of the magnetization M in the YZ plane. And the last remark here is the magnetization is threaded in the macroscopy models in which no spatial variation and magnetization is allowed. That means M does not change as external field and oscillating field varies. It means that we don't expect any change in the x direction of the magnetization vector. So by assuming the previous assumptions, these assumptions allows us to find the terms that we want to introduce to the LLG equations. So the blue dash remark allows us to separate magnetization into a static part and small independent components, and our magnetization with all components is given by like this. And from the effective fields and their energetic counterparts and the relation that connect the both, and knowing the relation that connects both parts, we can find all fields that has a role in this ferromagnetic resonance condition. And the yellow underlined remark includes having a small excitation field HRF added to the effective magnetic field acting on the sample. So it means that we can write our effective field as given. So we need to solve the LLG equations by taking these assumptions, and since we know the M and the H effective values, we can start with introducing these terms to the LLG equation. So LLG equations separated into 3 sets of differential equations, and since we know that there is no change in the x direction of the magnetization vector, we can cancel out this term, where our terms are separated into their subterms is like this, and these are the terms that what we have found from the previous analysis by taking the several assumptions. So solving this set of differential equations, which is the y and the z components of the magnetization, and here we can find a matrix which is a spatial matrix and called the polar susceptibility tensor, which includes the info about the susceptibility directions for each components, which is the y, y, z, z, y, and the z, z direction. After that, since we know that our damping term is in order of the 10 to the minus 2 or the 3, we can do this approximation to simplify our calculation, and we can use the convenient abbreviations that are used in the literature, which are given like this. So by dividing the HRF constant to the gas susceptibility, our susceptibility becomes like this. Includes both the real and the imaginary part. So we can separate we can split this into a real and imaginary part, and the individual parts as becoming like this. And the line with here we can find this, and here we can have a spatial relation that is called the Kittel relation that allows us to find the damping parameter and so on. Okay, so I want to show you a plotting example from that's taken from a thesis that studies and ferromagnetic resonance, and they use the parameters as shown in the presentation, and I repeated all the steps same by using the MATHEMATICA tool, and here the results I have found from the here. It is the XYY chi YY component, and it is separately plotted both by the imaginary and the real part, and it is the chi ZY component. They both plotted like this. Okay, so we have introduced ferromagnetic resonance theory and its analysis. So briefly, we will move through several headlines, which is about what FMR information is able to provide us. So the first thing FMR information is provide us, we can determine the gyromagnetic ratio. We can determine the effective magnetization and also the effective anisotropy fields from the fittings or the data analysis. So we can determine the damping term, which is the characterized to material, and it is important to find the damping parameter for several research fields, and it can be found like this. The learn more on magnetization damping parameter and its mechanisms, and the last one, learn more on underlying physical phenomena. It means that there is more phenomena that has a role on the occurring ferromagnetic resonance conditions. So it is important to learn more on underlying physical phenomena to learn more on the microspin models that has a role in this ferromagnetic resonance condition. So here I want to show how to determine the gyromagnetic ratio. It is my previous analysis that I performed through one of my measurements I have taken from our spin lab, where the gyromagnetic ratio can be found from the fitting of the Kittel curve that I have shown in the previous slides. So we can determine the damping parameter as a result of the preceding the analysis furthermore, and we can find the damping terms for a given material like this, by using the mathematical representation between the delta frequency and the damping parameter. This delta frequency terms comes from the every individual resonance conditions term, and by calculating all of them, we can find the damping term. So how to measure FMR? In this section, two of the FMR measurement techniques are presented. In this presentation, conventional FMR and vector network analyzer ferromagnetic resonance are introduced. So we first start with our conventional FMR technique. Measurement techniques of FMR can be classified by their mode of detecting magnetization here by saying that their mode of detecting magnetization, the mode can be electrical mode or the optical mode, and our conventional FMR and the vector network analyzer FMR method uses the electrical detection method. So in this method, an electromagnet provides an external magnetic field which varies in intervals, also is swept while the power reflected by the cavity is monitored. The power reflection, this power reflection terms means that our mode of detecting is the electrical mode. So when the FMR condition is met, there is a strong increase in the absorbed power, which is in a relation with the field derivative of our power, the power terms of our microwave source. So here we can see if the power input is like this, and we can see the Lorentzian shape in our power output, and it is our loss in the power that is reflected in when the FMR condition is met. So another and a modern technique is the vector network analyzer FMR technique. A modern version of the FMR is conventional FMR is the vector network analyzer ferromagnetic resonance technique. So instead of sweeping through an external magnetic field interval, vector network analyzer allows us to provide excitation fields in varying frequency intervals. So the difference between the conventional method and this method is that we kept the frequency. That means we use a single microwave source that is a single frequency constant, and we sweep through the field in the conventional FMR, and the opposite case is the true for this method. We sweep through a frequency interval and we kept the field constant, and we expect that for every frequency and the microwave source contribution, we would have an absorption peak for a certain field, applied field. So instead of using a microwave cavity in this experimental method, a coplanar waveguide is used to create oscillating field, which is the source of the magnetization precession. So how this occurs? When the FMR condition is met, there occurs an absorption peak at the resonance frequency. So intensity of absorption can be found from decreasing in transition coefficients, which is a broader extent, and it is not the subject I want to detail mention here, which is constantly monitored through a vector network analyzer system. So here we can see our shorted waveguide here, and our power input and the output will be different if a resonance condition met in our coplanar waveguide field. So I want to show the both measurements. One of the examples about both measurements. It is one of the vector network analyzer FMR measurement that is taken in our boost spin lab, and the other one is the conventional FMR measurement. These two measurements is connected to each other by a mathematical representation. So for every delta H is measured by sweeping the external magnetic field while keeping the frequency at a constant value, and the opposite case is true for the vector network analyzer ferromagnetic resonance measurement. We kept the field constant and the sweep through a frequency. So what is the difference between the both measurement techniques and what we want to observe through what the power reflection corresponds to? In the vector network analyzer FMR technique, we can see the Lorentzian shape because we kept the field constant and the sweep through frequency, and the power absorption directly results in our general data. But in conventional FMR method, since our frequency kept constant, our power reflection is correlated with the field derivative of our main data, as can be seen. This Lorentzian shape behavior, if we take this derivative of this shape, we can see the data that is shown in the conventional FMR measurements. So thanks for your attention and listening. That's all I want to talk about the ferromagnetic resonance. Thank you.